Hey everyone, welcome. I just started recording, so we're going to go ahead and kick things off. Hello and welcome. My name is Kathy Hoverman. I'm the moderator today, and this is the ASCE Environmental and Water Resources Institute and AFS Bioengineering Section's Joint Committee on Fisheries Engineering and Science. Since we're recording this, it's going to be available on our YouTube channel, and on our channel, you can see on the side here is where you can find that YouTube link. We've been doing these webinars since 2015. We unfortunately didn't start recording until just a few years ago, but we do have several of them up on our website, and we're excited to share those with you all. So please feel free to engage and look at these past webinars. This particular one is our third one for the 2024 series. If you received information on this through a colleague or a friend or somebody else and would instead prefer to get direct notifications, you can go on to our committee's website and under the webinar tab, go ahead and register under our email sign up so that you can receive direct notification the next time we have one of our webinars. And just in case you didn't know, the Joint Committee, we do a lot of different things. We don't just host webinars. We're also under new leadership. So really glad to have Mike and Amy and Theo as our executive team for the next 2 years, and see what they can bring to the table in leading us through. If you have interest in joining the committee, feel free to reach out to one of them. And then also you check out our website for the other things that we do. In 2025, we will have our 16th International Fish Passage Conference. The 2025 conference is in China at the Three Gorges University, March 30th through April 3rd. As part of that conference, there's an award that's given out called the Fish Passage Project Award. And the nominations for that award are going to be opening soon. So lots of times these are dam removal projects, but they don't have to be. But the idea is fish passage improvement. A big thing to note, if you're thinking about a project that you just did or that you know of, there needs to be monitoring results. So having that proof that there is good fish passage at the site is a key element. So something that may be just completed probably won't be eligible just because it hasn't been able to meet that monitoring criteria. You can check out more about the conference at the conference website. And we also wanted to announce the 2026 conference. The host location is UC Davis. So we are excited to see you in China and in California. Last bit of housekeeping is that we do have the next two webinars scheduled. So one more to finish out the 2024 series, and then our first webinar for 2025. We also have a few feelers out to get the rest of 2025 filled out. So we'll be able to notify everyone of those, hopefully at our next webinar in December. All right, so that is what I have. So I want to talk about our speaker today. Steve Amaral founded Biopassage Scientific Consulting after working for 30 years at Alden Research Laboratory in Environmental Engineering and Services. He has a BS and MS degree in Fisheries Biology, both from the University of Massachusetts. Over the course of his career, Steve has been extensively involved in the design, evaluation, and application of fish passage and protection technologies at hydropower dams and various types of water intakes. He's also led survival evaluations of conventional hydropower turbine design to pass fish safely, and several hydrokinetic turbine designs. He's also assisted with the development of theoretical models for predicting turbine survival. Much of Steve's fish passage experience has been focused on state and/or federally listed species or species of concern. In recent years, he has led several studies investigating technologies for reducing turbine entrainment of silver eels and has worked on the development of desktop models for estimating turbine and total project survival. In addition to his experience with aquatic resource impacts at hydropower dams in North America, he's also worked on fish passage or protection issues for projects in Estonia, France, England, Romania, Serbia, New Zealand, Brazil, and Cambodia. That's a lot, Steve, and I'm excited to hear what you have to share with us today. So I'm going to hand it over to you, and then just one comment for the listeners here. Feel free to drop in questions into the chat box at any time. However, we won't go over those questions until the very end, but please go ahead and start dropping those in as you come to them. Steve, all you.
All right, thank you, Kathy, and good afternoon, everybody. Thanks for taking the time out of your busy schedules to sit in on this presentation, and I'd like to thank the Joint Committee for inviting me as well to talk today. So I think the issue that I'll be covering today is obviously a really important one. One thing as a consultant in the past that we're often told to do when we're doing kind of BD and marketing with potential clients or existing clients is ask them what keeps them up at night. And I think if you ask a lot of hydropower dam owners, Eel Passage is probably one of those things that's near the top of the list as far as what keeps them up at night. And I would say that's true for you know, even some of us other folks that work for the agencies and consultants as well. It's a big issue. It's an important one. There are a lot of challenges to it. I do want to mention, you know, I do have my own consulting company now, but obviously anybody that knows me and the work I've done, I've spent 30 years at Alden Research Laboratory, which is now Verdantis Flow Labs, and I feel like I definitely need to recognize that as, you know, all of the work that I performed, lab and field studies and many other things, you know, I've worked on with my colleagues at Alden. And some of the studies that I'm presenting today, obviously, are going to be the ones that we did, you know, the team at Alden worked on. So I do borrow a lot from other researchers. I've gone to the literature and I've reached out to some other folks working with Eels and have incorporated that into my presentation. But it is a pretty high level look at downstream passage, and hopefully it's a lot of food for thought and get people talking and thinking, and maybe learn a few new things, and I look forward to any discussion and questions towards the end. So I'm gonna basically have divided my presentation into sort of three main things with respect to downstream passage. One is bypassing turbines. So what are the technologies that have been investigated to keep fish out of turbines, get them to bypass system, go to the spillway, operational measures that may be used to reduce entrainment, and then a lot of stuff that's been in the news lately about the fish safe turbines. Then I'll look at turbine passage and injury and survival, and that'll focus on lab data, field data, and some estimation methods that are currently being employed. And then briefly talk about total project survival modeling. So what is, when you look at all the potential passage routes of the eels moving downstream, what's a way of estimating that, particularly for if you're not doing field studies, a desktop approach. And then finally, just what I think are sort of the key takeaways from today's talk, and then what future efforts may look like. So with that, I'm going to start with a couple of videos. I think it's important to remind everybody, you know, sort of what we're up against with eels. They're a very unique species, obviously, and not like anything else that we try to protect from turbine entrainment. So this first one on the left is a study conducted at Alden with WPI and funded by EPRI. And it was with perpendicular bar racks. There's a bypass located on the left side here. This is a 3/4 inch rack, and I'm going to talk more about the data from this study in a second. And you're going to see this eel approach the rack, interact with it, and eventually become trained through it. It does a little bit of searching, poking around, and then eventually it's going to stick its head through the bars and make a real effort to get through. So gets its head through and it's gone. So yeah, that's the type of behavior we have to deal with when we're trying to think about how to keep these guys out of turbines. There is hope, and this video on the right is a goods in camera from a flume study conducted at Alden. And I'm sorry, this is the same study, but at night with all the lights out. And this is the rack right here. This is the bypass here. You're going to see an eel come down on the rack and right here, and then it goes over and does go into the bypass. So there is some guidance there. Narrow space bar racks, I'm going to start with them and angled screens and louvers. And first off, the Fish and Wildlife Service has developed some design criteria with respect to eels, and I guess these would be applicable to juvenile Alicines as well. But 0.75 inch clear bar spacing, less than 2 feet per second, max approach velocity about a foot in front of the intake, and an angle no greater than about 45 degrees to flow. The facility you see on the right is the Holyoke Canal louver array with the bypass at the downstream end. And this has been tested with eels and likely has a guidance efficiency of about 60 to 80%, and that's a 2-inch spacing on it. And there's at a 15-degree angle, so it's a very long sloping rack towards that bypass. In Europe, they've been using some incline rack and screen designs. Typically, they use 10 to 20 millimeter clear spacing, so that's about 0.4 to 0.8 inches. They have recommended about 1.5 feet per second or less max approach velocity, and with respect particularly to these incline designs, angle of about 35 degrees or less. These have been installed at several sites in Europe, and there have been a couple of installations in Canada, and I believe there also have been a couple of installations in the US. Going back to the bar rack study that we did at Alden, we looked at 2 spacings, basically to compare the 1 inch that had been recommended up to that point for juvenile salmonids and salmon smolts, and then the 3/4 inch that was being recommended for eels. We also tested both these spacings at 2 different velocities, 1.5 foot per second and 2 feet per second. You can see the average length of the eels that we evaluated, pretty typical probably for New England rivers. And then you see the mean bypass efficiencies. And so not surprisingly, with the narrower spacing, you did have greater bypass efficiency than with the 1 inch spacing. And it did appear that the effective velocity was greater for the narrower spacing than it was for the 1 inch. So 69 to 72% for the 1 inch and 89 to 96% for the 3/4 inch. The test facility down here, we did release fish upstream. There was a wall here that kind of helped them stay on this side of the flume, so they interacted with the rack, and then you can see where the bypass was located. And then the picture on the right is just a dewatered snap of the test facility. Some of the interesting things we learned from this study, we were able to develop these curves that show eel exclusion, physical exclusion by length for the 2 different spacings. What we did find out was that eels could have head widths, which is the most incompressible part of their body, that were up to 1.3 times the bar spacing and still fit through. They basically would have to have a head width greater than that ratio of 1.3 to have 100% physical exclusion. However, we did note quite a bit of behavioral guidance, and here we have the two test conditions, the spacings and velocities, and then broke it out by length bins for each set of test conditions. You can see what the bypass efficiencies were. And then we also put in the percent of fish for each of these size groups that we consider to be physically excluded. So in this first test, only 4.2% of the fish were large enough to be physically excluded, but we still had 94.7% bypass efficiency. You can see we got up to the larger sizes when 100% were physically excluded. Obviously, they wouldn't be going through. And then with the 1 inch, we had lower bypass efficiencies, but they still were higher than you would expect just based on physical exclusion alone. Moving on to behavioral deterrents and guidance systems, there's been a lot of work done with these technologies since I would say at least the 80s. A lot of focus on light, both continuous and strobe. A lot of testing with sonic and infrasonic sound and vibration. More recently, there have been studies with electric fields, turbulent and accelerated flow paths, and then EMF. One of the studies that myself and the folks at Alden were involved with was for the Eel Passage Research Center, which is a collaboration of power companies and agencies from Canada and the US involved with the St. Lawrence River. They were trying to identify potential methods to guide eels at the Iroquois water control structure, which is upstream of two big dams on the St. Lawrence. The idea would be if you could get them to a location across this structure, trap them, and then haul them downstream past the two projects. And both of those projects, because of their size, really it's difficult to design anything that would be effective at the site. And they decided that the water diversion structure was a much easier facility to do this type of thing at, even though this water control dam is about almost 1 kilometer wide. Anyways, we did do testing in our large flume at Alden, and we looked at electrical guidance and a flow velocity enhancement system. Released fish, eels at night with 3D acoustic tags, and then tracked their movements and collected them downstream to see if the systems could guide them and to what we call the bypass collection bin. Unfortunately, the results were pretty inconclusive, or the devices were determined not to be effective, and they weren't pursued further. I think there was some additional testing with the electric field that kind of went back a step just to see if there were certain aspects of or parameters related to the field that could be developed as being effective. But I think that testing done by the Connie Center and folks in the UK didn't produce anything positive. We also tested vibration and EMF in the lab study in a smaller flume. We didn't see any effect of EMF, but we did detect some avoidance behaviors for vibration. What the folks at the UPRC did was eventually turn to light, and you can see an installation of a light-guided light array that was installed upstream of the Iroquois Dam. And they have done some extensive field testing with acoustic tag fish for that study. And I believe they're currently working on the report, so no results necessarily to report right now, but maybe sometime in the near future. Moving on to bypass systems, we have surface weirs, submerged entrances, mid or near bottom. There's a zigzag horizontal conduit that was developed by a company in Germany, and then closer to home here at the USGS Connie Lab, Alex Arrow and his colleagues developed this what's called an Eel system, and I'll talk about each of these in a little more detail. What you see on the right is a downstream passage facilities that were developed by Alden and Kleinschmidt for the Holyoke Dam. And this is obviously for a combination of species, but it includes both the surface bypass and then a mid and bottom bypass for the more benthic species, which would include eel and sturgeon. So Alden did a evaluation of the Plowwise zigzag system that included both lab and field testing. This was funded by a grant from the U.S. Department of Energy Water Power Technologies Office. We had teaming partners that included Blue Leaf Environmental and Lakeside Engineering. For the laboratory evaluation, we evaluated both the Plowwise zigzag and then also these vertical systems that were developed by Lakeside Engineering, John and Eric Truby. And we had, this is a 20-foot wide flume, so it's really a nice simulation of an intake with full-scale bypass systems installed. We tested both with 1-inch and 2-inch bar spacing. We did test with a 16-inch per plate overlay on the lower portion of the rack and without it for one test. And then we looked at entrainment and bypass efficiency. The first test we did both bypass systems, 2-inch rack, no perk plate. You can see the bypass efficiencies were relatively low, less than 50%. We then did a test with the zigzag only, added the perk plate, and we see that the zigzag system had a 75% efficiency. So the perk plate seemed to help slow down eels moving through the rack and gave them an opportunity to find the bypass openings that are in the zigzag. We did do the vertical bypasses only as well with the perk plate, and we see an increase there with the well, I'm sorry, not a great increase in bypass efficiency, pretty low. So it seemed like the zigzag was doing most of the work there. However, when we went to the 1-inch rack and tested both bypass systems, we did go up to 91%. So very positive results there. And even the vertical bypass systems perform much better. This is a great system in that it uses very little flow, only a CFS or two. Not a huge footprint, fairly easy to install. It has these basically 2-inch openings that the eels find and go through. So the next step, based on what were positive test results with the 1-inch spacing, we did go to a field site. That was kind of supersizing our test flume, had a nice intake channel down to racks in front of 2 turbines. Unfortunately, only one of the turbines was operating for the testing, but we did, the Trubies did install the system here across the whole intake. We did put an overlay on just over 1-inch spacing on the operating turbine, and we did test with that and without that overlay for the reduced spacing. And this was on the natural river up in New Hampshire. The results weren't as good as we saw in the lab. We did 4 separate releases with 3 with the narrower bar spacing, 1 with the larger 3-inch existing spacing. We looked at different gate openings for the turbine, and you can see our releases. High entrainment rates for most of the conditions. We did have a fair proportion of our test fish return upstream and probably passed downstream over the spillway, so that reduced our sample sizes significantly. The highest efficiency we saw was 33% with the narrower bar spacing and the lowest flow through the turbine. You can see our setup here with the acoustic receiver arrays in the channel and where we release fish, where the yellow dot is. Some of the interesting findings we did find with respect to eels, they did do some searching when they came to the intake. However, most of the fish were found at probably in the lower 2 to 8 feet of water depth. And that's where we would expect them, I think, at most projects. But they will search vertically, and that was one of the reasons for developing that vertical bypass design as well. This is probably the reason for the poor performance. We have high velocities. This is a CFD model done by Alden. You can see a section here with the flow moving from left to right, zigzag system on the bottom, and then the intake rack. And you can see that the velocities get up to almost 4 to 4.5 feet per second in some areas, and that simply is just too fast for the fish to overcome and not being pinched or trained. So a better sight, without those kind of velocities, this system might work better. And there is a system installed at a project in Connecticut, the Upper Collinsville project, which was basically an abandoned site that was completely rehabilitated to produce power, and they put in a pretty nifty bypass system for shad herring and eels. And although it's a zigzag system, this is not constructed by Clawa. It was done by Wasserkraft. But you can see they have a horizontal 3/4 inch frac. They have the zigzag system for eels. They have surface and deep bypasses. You can see the surface spill here. This is actually the outlet right here for the zigzag system, and then there's a collection tank where they take the eels out, can handle them, count them, and then they put them into a little chute to go back to the river. A few more pictures of this system. You can see the discharge from the surface bypass, isolation gates upstream of the rack. Here's again the rack. This is I believe a cleaner for the rack that will push debris down this end and out the sluice. You can see the zigzag on the bottom. The bypass from the zigzag, clear pipe here, and then it discharges into the tank, and then fish can be put in the descent. Out to the bypass beach. They have not done any evaluation of the effectiveness of this system, and from what I was told, there are no plans to actually test it at this point. The airlift bypass system was developed by the Conti Center by Alex Arrow and his colleagues, and it basically is a low-level bypass with a riser that's filled with pumped air. It creates a current going up, and the fish would enter at the bottom and then go up and discharge in two of these applications here into a collection box where they can be removed and put downstream. It was installed at 2 water supply reservoirs, and you can see the number of eels that were collected in the system during the years that it's been in operation. All right, so moving on to spillway passage and survival. Spillways in existing gates can often be used for safe downstream passage. At many sites, survival rates will be greater than they are for turbines, likely exceeding 95%. However, you do need sufficient flow over the spillways. I'm not sure we really know what is required for eels. But in order for them to pass, there probably needs to be somewhere, 3, 6, 9 inches, something that could be investigated. I know that there are requirements for shad, herring, and salmon as far as minimum depths over the crest. Typically you would have to do an assessment of the spillway design to determine how fish friendly it may be, just by looking at it, the flow going over, the hydraulics, turbulence, what the fish are landing on. And then based on that assessment, you may want to do an evaluation of survival. There's not much you can do about fish passing over spillways, obviously. Eels go out with typically pulses of flow, so you're likely having a spill event. You can't really keep them away. But when you have to estimate total project survival, you want to make sure that component of it is accurate. So there have been a couple of spillway survivals done, and data I included on this slide is from an evaluation at Turner's Falls, First Lakes generation complex there. It includes Northfield Pump Station, Cabot Station, and a couple of smaller units in the canal. But certainly the gates at the Turner's Falls Dam potential passage routes for eels moving downstream. This table was pulled from the Feinsman, Gomez, and Sullivan report. Normandy did the testing using balloon tags. They evaluated the turbines and the Basco gates. You can see here in the highlighted rows, Basque-Gill Gate 1 up top and Basque-Gill Gate 4. So this is Basque-Gill Gate 1 here, Basque-Gill Gate 4 would be on this side. They did releases at 3 different discharge rates for each gate, and you can see a combined estimate of survival. You have immediate 1 hour survival and total survival after 48 hours. This 82.9 looks a little suspect given the 3 flow rates had higher survival, so I'm not sure if that's a typo, but you can see it range from about 85 up to 88% for the Basque-Gill Gate 1 and 83 up to 90% for Basque-Gill Gate 4. I'm sorry, 93.2%. Interestingly, the units at the downstream end of the canal at Cabot Station had survival rates of 96%. So you're actually getting better survival through the units than you are over the gates at this location, which may be the case at some projects. These are Francis turbines, and I'll be talking more about the high survival rates through Francis turbines that we've seen at some projects. Another study that I was involved with that was conducted by Alden for the Woonsocket Falls project in Rhode Island. It's owned by the city of Woonsocket, but operated by Thunder Mist Hydro. Small project with a 10-foot dam. It's a Corps of Engineers dam. The intake to the turbine is further upstream here. And the plan here may be for nightly shutdowns and then allow eels to pass over the spillway. Fish and Wildlife Service requested the spillway survival study. It's kind of a unique approach we took in that there wasn't easy access downstream here for a balloon tag effort. As far as getting people down there, certainly no boats or anything like that. And it was, again, being a small dam, you can see there's a sidewalk up here. It's the public walks right by. And then there's this wall down to the base of the spillway. So what we ended up doing was we built a pipe here and we put tethers on fish and attached them to a rod and reel and fishing line, released them through the pipe over the dam. And then as they came over the OG, we picked them up with the fishing line and put them into this net and then pulled them up. And you can see them being emptied out here. So this fish here you see on the right is actually tethered to the fishing line as it's going over the spillway. We looked at 2 flow conditions and we had survival rates of about 93 to 98% for an average for the flows combined about 95%. I will comment here that we did get the eels from the bait supplier and they were in pretty poor condition, showing external injuries and sores. And we had some mortality of fish that weren't even tested. I think with healthy fish, we may have seen closer to 98 to 100% survival for this test. All right, moving on to operational modifications. Nightly shutdowns are something that can be done 6 p.m. to 6 a.m. for the entirety of the specified downstream eel migration period. You also may be able to do targeted shutdowns based on precipitation events. Reduce generation, so you're reducing flow and hopefully reducing the number of fish that go into the turbines. Bypasses if sufficient spill will be needed to get the eels downstream, and there have been some work done with models to kind of predict the peaks and to help with the modification and operations. A lot of this work has been done in Europe, and you see an example here from some projects in Belgium where they basically have reference sites, look into migration surveys, environmental cues, and then develop the prediction models and then can apply it on a wider basis. Moving on to turbines, there have been several developments with fish-safe turbines that are very applicable to eels. The Alden turbine, some of you may be familiar with, it has not been installed anywhere, but it was tested with eels in the early 2000s in a pilot scale facility. But basically it's designed, it's got a few blades, so very wide spacings, no gaps between the blades and the outer ring or the hub. and it was designed for, to reduce damage and pressure and shear. It is a, radial flow unit like Francis turbines, but you can see unlike Francis turbines, which have 12 to 16, 18 blades, it's only 3. So again, those wide gaps between the blades to reduce the probability of strike. And then also thicker blade leading edges that help reduce strike mortality. We think that survival for that turbine could be 98% to 100% for silver eels. I can't imagine most people have not seen any news on the developments with the Mattel RH2 turbine. H. Schneider provided me with this slide and a couple others. They've had some very successful testing with this unit that's been evaluated in their test facility in California. You can see the conditions here, 10-meter head, 55-centimeter diameter, 667 rotational speed, and they had 100% 48-hour immediate 48-hour survival. So these slanted curved blades, you can see the eel passing through. Despite the high rotational speed and the small diameter of the unit, the eels were able to get through with 100% survival. Mattel is now working on developing these turbines for hydro modernization at a wide range of projects with respect to project size, head, and flow. They're expecting greater than 98% eel survival for these full-scale systems. And just a couple of conceptuals here for different designs of these units, including a Francis turbine with fewer blades. But you can see what the theoretical estimates, which are based on CFD modeling and the lab data. So there are expectations for these types of units if they are installed. Very, very promising and good results. There are a couple other fish safe turbines that have been developed by Andritz. This one here on the left was installed at a project in Belgium on the River Meuse, and then there is another one that was installed at a project in Germany. I believe these have both been tested. I think normally there are at least some testing of the Monson project. However, they're still working up the data, and there weren't any results available when I checked in on these projects. There are a number of low head turbine designs like the Archimedes screw, the VLH, and this Nyhouse turbine. They have been developed for heads typically less than 30 feet and some of them for less than 12 feet. But there have been testing done at least with these 3 designs, and again, very promising 98 to 100% survival of eels going through these units. All right, now that I'm through all the sort of options for downstream passage technologies to improve survival of eels, I'm going to take a little deeper dive into the turbine injury mechanisms and survival studies. And a little bit of history. This stuff has been going on at least over the last 30 years, but even longer than that for some of the field evaluations. But there were some blade strike tests done in '92 with European eels. Some of the first field tests done in the US were on the St. Lawrence project, including the Bohan Noir, which had a Kaplan, and the Francis turbine. Moses Saunders upstream of Bohan Noir, balloon tag studies conducted there. Alden did the pilot scale testing with its fish-friendly unit and 2 size groups of juvenile eels. Gomes and Larineer compiled the field data from European studies and some of the US and Canadian evaluations, and developed some nonlinear regression models for predicting survival. There was some laboratory blade strike tests conducted by Oak Ridge National Lab and by Epri and Alden. Field evaluations of low head turbine designs were conducted, and again, 98 to 100% for some of those. More field testing was done in France for 3 different units by Normando. And then there were field survival testings for many of the FERC relicensings that were conducted recently, both Francis and Kaplan type units in the Northeast. PNNL did some barochannel and fluid shear testing with eels, and the big finding there was that they weren't as susceptible to damaging pressure and shear levels compared to other species, and they concluded that strike and grinding were likely the primary mechanisms for eel injury going through turbines. Then, of course, Mattel and its RHD turbine development and the evaluations that they've done with their facilities in California. So just to get everybody on the same page as far as the two different primary turbine designs we have are radial flow units like the Francis turbines on the left, and then the axial flow unit on the right, which would be a Kaplan or a fixed blade propeller. So fish entering the scroll case, moving down through here axially, the eels moving through here, the scroll case, and then entering the unit radially. This is the results from the Alden testing in the lab with a pilot scale runner, 40 feet head, 240 feet RPM, best efficiency. These are the species that were tested. These are the non-eel species. You can see the relationship between length and survival. It's what you would expect. The longer the fish, the greater probability of strike and mortality. However, when we put the eel data on here, it's kind of off the chart, and it's much greater than it is for the other, much greater survival than it was for the other species. So 100% immediate survival for the two size groups, and then 99.6 for the smaller fish, and 98.3 for 96-hour survival. So keep in mind, this is a radial flow unit like the Francis turbines, which we've since determined eels do much better going through. But with only the 3 blades, it's got the much wider spacings. I've already talked a little bit about the Mattel unit. They did do testing with two different settings of turbines, and got pretty much 99 to 100% survival. And yeah, so a couple observations from blade strike. We had the high survival rates for Alden and Mattel, which indicate basically few eels are being struck and or they are being struck, and the survival is very high. And I would say for the Mattel lab test, where you had a very small diameter unit, most of those fish probably are being struck, but because of the blade design, the survival is extremely high. Solomon and Turnpenny from blade strike studies concluded that the sinuosity of fish is a way of reducing the effective length exposed to blade strike. So this would reduce blade strike probability, and certainly you can see in the right-hand pictures that's something that eels can do very well, ability to curve and bend easily. Blade strike tests have determined that eels are more resistant to strike damage than other species. And then it's been shown that 60% of the eel body can be classified as tail, where for which blade strike results basically no injury and mortality. This graph here is from the PNNL report, and it demonstrates the 50% mortality based on strike velocity, so 8 meters per second up to 20. And you can see the susceptibility of fish at the different velocities, and then you get to eel, which is way down at 20 meters per second. So clearly showing that it's less susceptible to the blade strike injury compared to typical bony fish. And then as far as that sinuosity, I took these frame grabs from one of the Mattel high-speed videos, but you can see the eel entering and going by the blade and curving and really reducing its effective length as it's going by the blade, so that would reduce strike probability. So I mentioned that Gomes and Lanier had compiled a bunch of field data, and they had 51 tests from 19 projects. They created these best fit regression models that kind of incorporated eel length, runner diameter, rotational speed, and turbine and or turbine flow, and the numbers of blades. Was not identified as effective, but that's because mainly most units were 4-bladed. However, they probably could have looked at blade spacing, and that would have given them a better parameter, and that probably would have shown some correlation. So Alden did sort of update the analysis of Gomes and Lanier by including tests with wicket gate openings less than 70%. We estimated the actual flow rate going through each gate opening. We included blade spacing as a parameter. We added survival data from additional sites where balloon tag studies have been conducted. And we also added other turbine designs, but that just allows you to look at each different turbine design and evaluate it separately. And then we did, for Kaplan propeller turbines, develop some multiple linear regression models to predict turbine survival. This just shows kind of a summary of the different turbine designs that are in the database and the studies that were done, most being netting or netting and telemetry, but then more recently the balloon tags done with both Francis and Kaplan units. Some of the regressions we did on the individual parameters showed sort of their relevance to survival. So in this one, we can see blade tip speed, there's an R squared of about 0.12, not very high. So it doesn't explain a lot of the variability. The same with gate opening, no relationship there between that and survival. And even eel length didn't produce a great relationship with survival. And that might be in part due to the fact that the eels are constantly changing their length as they're passing through the units. The two that stood out were blade spacing, at the tip, which is a relative measure of the space between the blades that the eels have for passing through. So relatively good correlation there, and then rotational speed. So those two have a big effect on strike probability for eels passing through the turbine. These are field tests conducted with just balloon and float tags. The columns that I've highlighted are the rotational speed and the blade spacing. Essentially, you're increasing in rotational speed, decreasing in blade spacing, and then decreasing in survival. However, at the lowest blade spacing and highest RPMs, we did see that at Vernon, they got pretty good survival, not necessarily something we would have predicted. This is just a graph of that data. So you have the rotational speed in the blue increasing, the blade spacing decreasing, and survival typically decreasing with those parameters. We've included both the regression model results and the field data, so you can see that the regression model tracks pretty well until we get to those Vernon sites. And we also included two sites, Willow Island or Roanoke Rapids, where we just did the theoretical or the linear regression estimation. These are the Francis units that were evaluated with balloon tag studies, although the Boheim War was a float tag. Again, RPMs increasing, but maybe bouncing around a little more than with the Kaplan units, and then blade spacing decreasing. We do see, again, a general decline in survival. However, if you go down to this unit with a low RPM, but a small blade spacing, you did have a good survival rate there. So these numbers look a lot better than the Kaplan turbines, which have fewer blades and greater blade spacings. And this is a graph of the blade spacing for Francis turbines and survival, and then the Kaplan or propeller units here. This would be completely opposite for any other species, but for some reason, eels have been able to get through the Francis units with less damage and mortality. This is a graph showing tip speed provided by Mattel and different types of turbines and the general decline. One of the things Mattel has been trying to deal with is how you can use information we know with respect to strike probability and survival and apply it to a fish-friendly unit where it may not necessarily fit into those theoretical models. So how can you potentially determine something might be fish-friendly, or look at fish-friendly units and come up with an accurate theoretical estimate of it? So you can see the Mattel turbines up here, high tip speeds, which could be an indicator of strike velocity. And then for these other more conventional units, greater tip speed generally lower survival. The theoretical models, so this is one that is basically predicting the ability of fish to get between two blades without getting struck. This is the one that Alden uses quite a bit, and it is also incorporates blade strike tests that estimate mortality if a fish is struck based on the fish's length, strike velocity, and the ratio of the fish length to the blade thickness. This is very similar to the Frankie method. Here's the desktop model that was developed by Fish and Wildlife Service that a lot of people are familiar with and using. However, you can't use it for Francis turbines, basically of what we've seen with eels, and it would be a underestimation. I would say it's also an underestimation of survival for Kaplan and propeller units, but Brett Tyler and Jessica Pica did develop a lambda or mortality coefficient based on the field data from Jones and Lanier. 0.4 is what they've recommended to apply to the theoretical model for eels. However, there is a bit of variability in the data, and it is one number that you're now applying to every unit and every length of fish. So there has to be some caution there when using that model.
Hey, Steve, I just want to jump in real quick. We have about 8 minutes left in total time. So if you want any time for any questions, hopefully we're coming. You can grab it quick here.
I'll try to wrap it up in a couple of
minutes.
minutes.
All right. Thanks.
I'll skip through these next two slides kind of quickly and not get into details here, but there is a desktop approach for estimating total project survival, and basically looking at the flow probabilities, passage route selection, and the survival for each route. And it's not perfect, but I think it is a good tool that can help with assessments. And this graph just shows where it was done at one site where they compared two different bar spacings and what the survival over the flow range may be. So getting into the end of the talk, my takeaways, methods for safe downstream passage, bar spacings and racks and screens should be selected based on the level of exclusion required to meet total project survival. However, less than 1 inch may be needed, but there may be sites where 1 inch may be adequate. Max approach velocities should be less than 2 feet per second. There's considerable evidence with respect to light being a method for repelling eels. I'm not as high on some of the other behavioral deterrents, but maybe there's more work that could be done here to improve pushing fish away from turbines and toward bypasses. There are several eel-specific bypass designs that have been developed and tested and should be considered when you're designing your downstream passage facilities. Fish-safe turbine designs are available for a wide range of projects, heads, and flow rates. With respect to turbine survival, eels have higher survival than you would expect based on their length alone. Pressure and shear are likely inconsequential for most turbine designs, particularly for low to moderate head projects. Contortion and sinuosity likely to lead to lower blade strike probability and strike mortality. For each turbine type, excluding the fish-safe designs, rotational speed and decreasing rotational speed, increasing blade strike produce greater survival, and eel length likely has a lesser effect. Survival typically decreases with increasing tip speed due to higher strike velocities, and the fish-safe turbine designs do incorporate features that reduce strike mortality at these higher tip speeds. Several fish-safe designs and low head turbine design, both for larger projects and for low head projects, are currently available, and I've shown rates as high as 98 to 100%. And survival is higher going through Francis units than is for propeller units, likely due to the way the eels are entering the runner and interacting with the blade. And then theoretical blade strike models probably shouldn't be used with eels, and maybe the linear regression models could be more appropriate. Finally, future efforts, basin-specific migration data would be helpful, improve models for predicting peaks and downstream movements, route selection, spillway survival rates. We could use more information there. Full-scale testing of the fish-safe turbines, hopefully that's going to happen soon, particularly with the nacelle units, and then validation of the desktop models. And I will go ahead and end it there. I did have a couple of slides on what a collaboration of all the organizations that have been involved in eel testing may look like. But that will be included with the slides when they're made available to folks. So, Kathy, I guess that wraps it up there, and we can go ahead and move on to any questions or comments.
Sure. Yeah. Great. Well, thank you, Steve. I can tell you've got a lot of information to share, and I'm sorry we don't have even longer time for you to educate us all on this, but thank you. So there's two comments in there right now. One's a comment, one's a question. So we might have time for maybe one other one, but the first one, somebody commented that the Clawa systems don't work. And that I guess their experience is that they're clogged with zebra mussels. So do you want to comment on that in any way?
Sure. I mean, they've had mixed results. I would definitely agree with that, based on our own experience with them. It would be interesting to see how the one in Connecticut performs. The eel entrainment should be really minimized with the narrow space in there. It's a small intake, so there's, ample opportunity for the eels to find it. Yeah, definitely zebra mussels would be an issue for projects where they occur, and debris management of those systems can be a problem as well. So definitely factors that you have to take into consideration if you're considering a technology like that.
Yeah. Okay, it sounds like there's a couple questions within this one. How much did the Upper Collinsville exclusion and bypass system cost to install and cost to maintain? How many kilowatt is the plant? And if understood correctly, there is no plan to validate the performance. So the question is, why not?
Yeah, so I don't have the answers off the top of my head for the two first questions there, regarding cost and the generation output of the project. And what was validation. So I reached out to the owners of the project, and they indicated that there were no plans for effectiveness testing at the project. So, unfortunately, we may not see any data come out of that site.
Yeah. Okay, we do have 2 minutes left. Does anybody want to slide one more question in before we close out? Give this, all right. Looks like nothing else is sliding in here real quick. So I'll just take a minute to say, oh, there we go. Oh yeah, there's a little bit of echo. It's somebody said, but that's all right. So this is recorded. So everybody can come back and listen to it again and get some more information on this. Steve, thank you so much for presenting today. We really appreciate the time you took to put a presentation together for us, and obviously the time here today as well. So thank you so much, and we will see everyone again in December for our next presentation. Thanks all. Take care.
Thank you.